Standard conditions. We use something called standard temperature and pressure, and it's abbreviated STP for standard temperature and pressure. Standard pressure is 1 atmosphere, which is the same as 760 torr. Standard temperature is 273 Kelvin or 0 degrees Celsius. Those are the same. You need to know what standard temperature and pressure are. What they are is atmospheric pressure and the freezing point, melting point of water. So this is a set of conditions that's very easy to establish. If your container is open to the atmosphere, it's going to have standard pressure. And if you put it in an ice water bath, it'll be at 0 degrees. So this is really nice. Remember, most of these gas experiments were done long before refrigeration. And so regulating temperature of a gas was tricky unless you either had it in a pot of boiling water or in a pot of ice water. You couldn't keep the temperature the same that way. STP is very useful for making comparisons between gases because you've got volume, temperature, pressure, and number of moles of gas, and with all these different things that can change, it can be hard to compare two gases. So STP makes it easy to compare. Then we have this idea of a molar volume. The molar mass is the mass of 1 mole, right? The molar volume is the volume of 1 mole of gas at STP. And so this makes it easy to compare things. So at 273 K and a pressure of 1 atmosphere, you can calculate this, the volume of 1 mole at STP. So you put in 1 mole for N, there's R, here's standard temperature, and there's standard pressure, and you get 22.4. This is a very useful number. So the volume of a gas at STP is 22.4 liters per mole at STP. That looks like a conversion factor, doesn't it? It sure does. So 1 mole of gas, that's Avogadro's number of molecules or atoms of a gas, occupies 22.4 liters at STP. What the gas is doesn't matter. Doesn't matter if it's carbon dioxide or hydrogen or helium. The volume will be the same, and we call that the molar volume. It's important to recognize that 1 mole of different gases would have different masses, right? But the same volume. Volume will be the same. Temperature, pressure, number of moles, it's all the same, but one is going to weigh more than the other because the mass will be different. Same number of particles, but each particles weigh more, then the gas is going to weigh more. So an illustration of that. 22.4 liters, which 22.4 liters is a cube about this in dimension. So, it's a large amount, but like a big box. 1 mole of helium is going to weigh how much? 4 grams. 1 mole of xenon, 131 grams. And we don't need, 12 plus 4, 16. So 1 mole of methane would weigh 16 grams. But they're going to have the same number of particles, occupy the same size, even though the individual particles are different. This reminds me of a family vacation that we went on. We used to drive to Minnesota. Why we stopped is a very long story. But anyway, we used to drive to Minnesota to see my family in the summer. And I remember when we went through Wyoming. Wyoming is not very densely populated. At that time, which was about 10 years ago, Fresno had a population of about 440,000. And the entire state of Wyoming had about the same population. And that's not Fresno and Clovis, that is just Fresno, right? there's not that many people in Wyoming. And when you drive through Wyoming at night, you recognize that because you can drive for miles and not even see one farm light. I mean, it's like crazy dark. Gases are a little bit like the people in Wyoming. There's a lot of space between them. Okay? Now, a liquid is more like, or a solid, well, say a liquid. A liquid is more like people in an elevator. There, the size of the individual person matters. If you're a big person or you're a little tiny person, maybe a 2-year-old, right? You could fit more 2-year-olds in the elevator, right, than big 300-pound linemen from the football team. The size of the people matters. In Wyoming, there's so much space that the size of the people doesn't matter. The size of the gas particles doesn't matter. Xenon atoms are much bigger than helium atoms. Much bigger. Doesn't matter. The gas takes up the same volume because it's still mostly empty space. But it's going to weigh a different amount because each of these particles has a much higher mass than the helium does. That's one of those things that's just kind of weird because there's not a lot of things in real life that are like that. We can look at the density of a gas. We'll refresh our memories here. Density is mass divided by volume. We usually express densities of gases in grams per liter. We used grams per milliliter for liquids and grams per cubic centimeter, which really is the same thing for solids. But gases are much less dense, and so we use grams per liter so that the numbers are more reasonable. Well, we can calculate the density of a gas because we know what the mass of 1 mole of a gas is, right? It's the molar mass. So 1 mole has a mass equal to the molar mass, and at STP we know the volume of one mole of gas is 22.4 liters. So at STP, the density of a gas equals the molar mass divided by the molar volume. I don't recommend really memorizing that equation. I think it's better to just think about it. So examples. Here's helium. The density of helium at STP, it's the mass divided by the volume. And we're just saying, well, let's say we had a mole, just because that would make everything easy. 1 mole of helium weighs 4 grams from the periodic table. 1 mole of helium at STP occupies 22.4 liters. We do the math, we come up with 0.179 grams per liter. Nitrogen, N2. 1 mole of it weighs 28.02 because it's diatomic. Same volume, its density is 1.25 grams per liter. The density ends up being directly proportional to the molar mass of the gas. Don't have anything else to say about that. Calculate the density of chlorine gas at 758 millimeters of mercury and 35 degrees Celsius. We're getting there. We're getting there. I know where the stopping point is. It's mixtures of gases. Okay, so calculate the density. So then we say, well, what is density again? Density is mass over volume. You're like, okay, so we need the mass of this gas and we need the volume of the gas. They don't tell us an amount of gas. So we can pick the amount. We can do that because density does not depend on how much gas you have. Density is an intrinsic property of a substance. It doesn't depend on the amount. So let's just say 1 mole, because 1 mole is easy. So the mass of 1 mole of chlorine gas. What's the formula for chlorine gas? Cl2. Horses need oats for clear brown eyes. So the mass is 2 times the mass of 1 mole of chlorine atoms, which I believe is 70.90 grams. So the mass is 70.90 grams. That's just a nasty looking 7. What's the volume of 1 mole of gas? Well, it's 22.4 liters at STP, but is this STP? No, darn it, that would be too simple, wouldn't it? We're going to have to calculate it from our new friend, Pivnert. The volume is nRT over P. So I'm going to skip the whole table thing on this one. N is 1 mole, right? We decided that. And as long as we're deciding things, we're deciding it's exactly 1 mole. So 1 mole of gas, R 0.08206 liters, atmospheres per mole Kelvin. What's the temperature? 35 plus 273, right? Say it again, 308.15. And the pressure, it's like, it'd be too nice for them to give it to us in atmospheres. See this unit here, atmospheres? We need this in atmospheres. 758. Isn't this just like real life? You know, you just set out to do one simple thing, and before I can do that, I have to do this. And before I can do that, I have to do that. And pretty soon you've gone through, if you give a mouse a cookie, and you've gone all the way around and you're back where you started from, and you haven't accomplished anything. I'm sorry, but that's my life. It happens more at home than it does here, but good grief, it's just frustrating. But this is like, oh man, we have to do one more thing. It's okay, just suck it up and do it. So 1 atmosphere is 760 millimeters of mercury. So we just need to take 758 and divide by 760. You may say, yeah, well, they're so close. Well, yeah, but they're not the same. And so down here we've got 0.99736.842. Sometimes what I like to do is I just put it in there as a fraction, but, you know, whatever you like. Okay, so 1 times 0.08206 times 308.15 divided by 0.997. 36842 equals 25. Okay, this number should have, let's see, 3 significant figures. So I'm going to keep 2 extras. So that would be the last one. I'm going to keep those guys. And this is liters. I guess I could put the L there. And I'm going to underline that to remind, no, you can't underline with an eraser? What is wrong with this thing? 25.3, what did I say? 54 liters. $70.9 divided by 25.354 equals 2.7964, etc. So this rounds to 2.80 rams per liter. You can't just drop that digit. 2.80 grams per liter. Is that a reasonable density for a gas? Yeah, it is. 5,000 grams per liter, not reasonable. 0.0007, not reasonable. Any questions? Besides, can we go home yet? We're almost there. Molar mass of a gas. We're going to do this on Tuesday. We are going to experimentally determine the molar mass of a gas. One way you can do that is to heat a volatile liquid until it becomes a gas and measure the temperature, pressure, and volume of it, and then let it cool down, and you can measure the mass of it, and then we can use the ideal gas law and calculate the molar mass of the gas. It's really kind of cool. So what is molar mass? It's mass divided by the number of moles. Usually we think of it as the mass of 1 mole, but if you're not dealing with 1 mole, you figure out how many moles you have, you take the mass and divide by the number of moles. An organic chemist isolates a colorless liquid from a petroleum sample. Ooh, the suspense is building. She places the liquid in a pre-weighed flask, yes, I know I'm crazy, and puts the flask in boiling water, which vaporizes the liquid and fills the flask with gas. She closes the flask and reweighs it. She obtains the following data. Calculate the molar mass of the liquid. So you kind of have to step back from a problem like this and think about the big picture first before you get lost in all the digits. So molar mass. What do we need for molar mass? We need the mass and the number of moles. Did they give us any of that? Yeah, kind of. They gave us the mass of the flask and the mass of the flask plus the gas. So can we figure out the mass of the gas? Yeah, we just subtract them. So we're going to take 78.416 minus 77.834 equals, so the mass of the gas is 0.582 grams. Now we need the number of moles. Measuring the number of moles is not a simple matter unless you're dealing with a gas. Here we have a volume, we have a temperature, and we have a pressure. To get the moles, we're going to use PIV-NERT. Are these the correct units to plug into PV equals nRT? They are not. Well, let's fix them. If we take, I can't even read numbers anymore, 754 torr, we need to divide that by 760 to get atmospheres. And I'm going to carry extra digits because we don't want rounding errors. We're doing all this work, we might as well do it right. Yeah, atmospheres. What do we need to do that temperature? We need to add 273.15 Kelvin, and now the uncertainty is right there. I should keep track of it in this guy as well. It's right there. And the volume is in milliliters. We need liters. We need to, it's going to be you like that? 0.213 liters. We're multiplying by 10 to the minus 3. We're dividing by 1,000. Now we can use the ideal gas law. So number of moles of gas, PV equals nRT. This will be PV over RT. So pressure, 0.992105. That's an A. TM. Volume, 0.213 liters. Our dear friend, the ideal gas constant. Get out your calculators and calculate with me, please, because there's a thing that happens to some students when we do this one. .99 0.2105 times 0.213 divided by 0.08206, and then divide by 373.15. The answer is 0.00690116 moles. That should have three sig figs. Now, if you got a really, really big number, you're having issues with your calculator. Some students, they take this times this, they divide by this, and then they want to multiply by that because these two numbers are multiplied. Your calculator does not understand that. When you press the times button, it finishes all the rest of the stuff and takes this whole thing times 273 you really wanted to divide by. So if you find yourself not getting this number and that explanation didn't make sense, come to me and I'll help you out with that. So that's the number of moles. We're going to stick it in here, 0.0. Um, 0.582. Our final answer should have 3 sig figs. I'm getting 84.3 grams per mole. Is that a reasonable molar mass? Yes. What if I got 0.843 grams per mole? Is that even possible? No. What's the smallest molar mass we can have? 1.008, which would be hydrogen atoms, which, good luck getting those. It's probably going to be 2.016. So if you get less than 2, something went wrong. You also shouldn't get like millions or something like that. Okay? So now you should be able to do the pre-lab assignment for lab.